In the summer of 1940, Britain stood alone against Nazi Germany. The fate of the free world hung in the balance during the Battle of Britain. But there was a secret weapon, not a bomb or a gun. It was an engine, the Rolls-Royce Merlin. This is the story of the engineers who created one of history's greatest achievements, an engine that would power victory in the skies and change aviation forever. Our story begins in 1932, at the Rolls-Royce factory in Derby, England. The company was famous for building the world's finest luxury automobiles. But they also had a lesser-known division that built aircraft engines. The chief engineer of this division was a man named Ernest Hives. Hives was a practical engineer who had started as an apprentice. He understood engines not just in theory but from years of hands-on experience. Working alongside Hives was a brilliant designer named Arthur Rowledge. Rowledge had previously worked at Napier, where he had designed successful engines. Together, they formed a partnership that would change aviation history. In the early 1930s, aviation was advancing rapidly. Aircraft were flying faster and higher than ever before, but existing engines were reaching their limits. The British Air Ministry recognized that war with Germany was becoming likely. They needed a new generation of high-performance fighter aircraft. And those fighters would need engines more powerful than anything yet created. Rolls-Royce had been developing a line of engines called the R Series. These engines had powered racing seaplanes to victory in international competitions. They had proven that Rolls-Royce could build engines with extreme power output. But racing engines were not suitable for military use. They were fragile, unreliable, and required constant maintenance. A combat engine needed to be powerful but also dependable. It had to run for hours without failure in extreme conditions. Hives and his team began designing a new engine in 1933. They designated it the PV-12. PV stood for private venture. Rolls-Royce was funding the development themselves without government contracts. It was a calculated gamble that the military would eventually need such an engine. The design incorporated lessons learned from racing engines, but engineered for reliability rather than pure speed. It was a 12-cylinder engine arranged in a V configuration. Each cylinder bank had 6 cylinders, set at a 60-degree angle. This configuration balanced power output with compact dimensions. The engine would eventually become known as the Merlin, named after the small, powerful falcon, not the wizard. Rolls-Royce had a tradition of naming engines after birds of prey. The name proved fitting for an engine that would dominate the skies. Creating a high-performance aircraft engine in the 1930s presented enormous challenges. The engineers had to balance multiple competing requirements. Power output needed to be maximized while keeping weight to a minimum. Every pound of engine weight reduced aircraft performance. Yet the engine had to be strong enough to withstand tremendous internal forces. The cylinders would experience explosions thousands of times per minute. Temperatures inside the combustion chambers reached over 2,000 degrees. The pistons moved up and down at incredible speeds, creating massive stresses. Arthur Rowledge led the design of the cylinder block and heads. He chose to cast them from aluminum alloy for lightweight, but aluminum alone could not withstand the heat and wear. So steel cylinder liners were inserted into the aluminum block. These liners provided a hard, durable surface for the pistons. The cylinder heads were designed with careful attention to cooling. Water jackets surrounded each cylinder to carry away heat. The cooling system had to be efficient without adding excessive weight. One of the most critical design elements was the supercharger. At high altitudes, the air becomes thin, containing less oxygen. Less oxygen means less power from the combustion process. A supercharger compresses incoming air before it enters the cylinders. This maintains power output even at high altitude. The Merlin supercharger was driven by gears connected to the crankshaft. It spun at many times the engine speed, compressing large volumes of air. The design of the supercharger impeller was crucial. It had to move air efficiently without consuming too much power from the engine. Early prototypes had problems with the supercharger design. It vibrated excessively and sometimes failed catastrophically. The engineers spent months refining the impeller shape and gear ratios, testing different configurations, measuring airflow and pressure rise. Eventually, they achieved a design that was both powerful and reliable. Another challenge was the engine's lubrication system. Oil had to reach every moving part under all flight conditions. During aerobatic maneuvers, the aircraft might be inverted or in steep climbs. The oil system had to function regardless of the aircraft's orientation. The engineers designed a dry sump system with multiple oil pumps. Oil was stored in a separate tank and continuously circulated through the engine. Scavenge pumps collected oil from the bottom of the engine and returned it to the tank where it could cool before recirculation. By 1935, the first complete prototype was ready for testing. It produced just over 1,000 horsepower on the test stand. This was impressive, but the engineers knew they could do better. The real development work was only just beginning. Testing the Merlin engine was a grueling process that would span years. The test facilities at Derby ran engines continuously. Day and night, the roar of Merlins filled the factory. Each test run revealed new problems that needed solving. Early engines suffered from overheating and prolonged high-power operation. The cooling system was redesigned multiple times. Cylinder head gaskets failed, allowing coolant to leak into the combustion chambers. New gasket materials and designs were developed through trial and error. The connecting rods which linked the pistons to the crankshaft sometimes broke. When this happened, the engine destroyed itself in spectacular fashion. Metallurgists analyzed the failures and specified stronger alloys. The crankshaft had to be perfectly balanced to avoid vibrations. Even small imbalances at high RPM caused severe damage. Each crankshaft was individually balanced with extreme precision. Ernest Hives personally supervised much of the testing program. He had an engineer's intuition for identifying the root causes of problems. When others were baffled, Hives could often suggest solutions. His leadership kept the development program moving forward. In 1936, the first Merlin engines were installed in prototype aircraft. Flight testing revealed issues that couldn't be found on a test stand. The engine had to operate under constantly changing conditions. Rapid throttle movements, varying air temperatures and pressures. Vibrations from the airframe that interacted with engine vibrations. Test pilots pushed the engines hard, simulating combat conditions. They dove at full throttle, pulled high G maneuvers, operated at extreme altitudes. Each flight generated data that engineers analyzed for improvements. One critical breakthrough came from experimenting with fuel mixtures. The octane rating of aviation fuel affects how much the air-fuel mixture can be compressed before ignition without detonating prematurely. Higher octane fuel allows higher compression ratios and more power. Initially, the Merlin was designed for 87 octane fuel, but experiments showed significant power gains with 100 octane fuel. The problem was that 100 octane fuel was not yet available in quantity. Rolls-Royce worked with fuel companies to develop production methods. Meanwhile, they modified the engine to take advantage of the better fuel. The compression ratio was increased and ignition timing was optimized. These changes would prove crucial in the coming war. By 1938, the Merlin had evolved through several versions, each one more powerful and reliable than the last. The Merlin Mark II produced over 1,000 horsepower and was considered ready for production. The Air Ministry ordered the engine for 2 new fighter designs, the Hawker Hurricane and the Supermarine Spitfire. These aircraft would soon become legendary, and the Merlin engine would be their beating heart. As war clouds gathered over Europe, Britain faced a daunting challenge. The Royal Air Force needed thousands of modern fighters, and that meant thousands of Merlin engines had to be produced. But Rolls-Royce was a company accustomed to building hundreds of engines per year, not thousands. The production methods had to change dramatically. Traditional Rolls-Royce manufacturing emphasized craftsmanship. Skilled workers hand-fitted parts ensuring perfect tolerances. This produced superb quality but was slow and required highly trained personnel. Ernest Hives recognized that mass production required different approaches. Parts had to be more precisely manufactured so they were interchangeable. Assembly processes had to be standardized and streamlined. The company invested heavily in new machine tools. Precision grinders, milling machines, and lathes filled the expanded factories. Gauges and measuring instruments ensured dimensional accuracy. The workforce expanded rapidly as war approached. Thousands of workers were hired and trained in aircraft engine production. Many were women, taking jobs traditionally held by men. They proved to be skilled and dedicated workers. New factories were built to supplement the Derby facility. Crewe became a major production center for Merlin engines. Additional facilities were established in Glasgow and other locations. The supply chain became increasingly complex. Each Merlin contained thousands of individual parts: castings, forgings, machine components, fasteners, gaskets. Many parts were subcontracted to specialized manufacturers. Coordinating this network of suppliers was a massive logistical challenge. Quality control became critically important. Every engine had to meet strict standards before being shipped to the RAF. Each completed engine was run on a test stand for several hours. Power output, oil pressure, coolant temperature, all were carefully monitored. Any engine that failed to meet specifications was torn down and rebuilt. Despite the challenges, production ramped up impressively. In 1939, the Derby factory alone was producing hundreds of engines per month. By 1940, multiple factories were churning out Merlins around the clock. Workers operated in shifts, so production never stopped. The factories became targets for German bombing raids, but production continued even as bombs fell nearby. Workers showed remarkable courage, staying at their posts during air raids. They understood that every engine they built helped defend Britain. The scale-up of Merlin production was an industrial achievement, comparable to the engine's technical brilliance. It transformed Rolls-Royce from a boutique manufacturer into one of the world's largest aero engine producers. In the summer of 1940, the Merlin engine faced its greatest test. The Battle of Britain would determine whether Nazi Germany could invade the British Isles. Hitler's Luftwaffe launched a massive air assault. Hundreds of bombers and fighters attacked RAF bases and British cities. The goal was to destroy the Royal Air Force and achieve air superiority. Standing against this onslaught were Hurricane and Spitfire fighters, both powered by Merlin engines. The Hurricane was a sturdy, reliable fighter designed by Sidney Cam. It was slightly older in design but available in larger numbers. The Spitfire, designed by R.J. Mitchell, was more modern and agile. Its elliptical wings gave it exceptional maneuverability. Both aircraft benefited enormously from the Merlin's power and reliability. The engine gave them speed to intercept German bombers and performance to dogfight with enemy fighters. One crucial advantage came from the fuel system. German engines used direct fuel injection, which worked in any orientation. The Merlin initially used a float-type carburetor. During negative G maneuvers like pushing into a dive, the carburetor would flood. The engine would sputter and lose power temporarily. German pilots exploited this weakness by pushing into dives. Knowing British fighters couldn't follow immediately, a young woman engineer named Beatrice Schilling devised a solution. She designed a simple metal disc with a hole in the center. This restrictor, called Miss Schilling's orifice, limited fuel flow. It prevented flooding during negative G while still allowing full power. The modification was simple enough to be installed in the field. Within weeks, RAF fighters had the fix and the advantage shifted. The battle raged through the summer and into autumn. RAF pilots flew multiple missions per day, their Merlins roaring overhead. Ground crews worked frantically to keep aircraft serviceable, refueling, rearming, and performing quick repairs between sorties. The Merlin's reliability proved invaluable during this intense period. Engines ran mission after mission with minimal maintenance. When damage occurred, they often kept running long enough to get the pilot home. Pilots developed deep trust in their Merlins. They knew the engine would deliver power when they needed it most. By October, the Luftwaffe had failed to achieve air superiority. German losses were unsustainable. The invasion of Britain was postponed indefinitely. Winston Churchill famously said of the RAF pilots, "Never in the field of human conflict was so much owed by so many to so few." But those few relied on the Merlin engine. And the thousands of workers who built them. The Battle of Britain was won in the skies, but also in the factories where Merlins were manufactured. The engine had proven itself in the crucible of combat. The Battle of Britain was won, but the war continued for years. Throughout this period, Rolls-Royce engineers constantly improved the Merlin. Each new version incorporated lessons from combat and testing. Power output steadily increased as the engine evolved. The early Merlin Mark II produced about 1,000 horsepower. By 1945, advanced versions produced over 2,000 horsepower. This doubling of power from the same basic design was remarkable. One major improvement was the development of two-speed superchargers. The original single-speed supercharger worked well at one altitude range, but performance dropped off significantly above or below that range. A two-speed supercharger had two gear ratios that could be selected: low gear for takeoff and low-altitude flight, high gear for maximum power at altitude. This dramatically improved performance across the entire flight envelope. Later versions incorporated two-stage supercharging. This used two superchargers in series, each compressing the air further. An intercooler between the stages cooled the compressed air, making it denser and allowing even more air into the cylinders. Two-stage Merlins maintained full power up to 30,000 feet. This gave British fighters a crucial advantage at high altitude. The fuel injection system was also improved over time. Miss Schilling's orifice was eventually replaced by a proper fuel injection carburetor. This eliminated the negative G problem entirely and provided better fuel metering under all conditions. Metallurgy advances allowed higher compression ratios. Stronger alloys could withstand greater pressures and temperatures. This translated directly into more power output. The propeller reduction gearing was refined for efficiency. The engine crankshaft spun at very high RPM for optimal power, but propellers work best at much lower speeds. The reduction gearbox stepped down the speed while maintaining torque. Improvements in gear design reduced losses and increased reliability. The ignition system evolved from magnetos to more sophisticated designs. Better spark timing and more powerful sparks improved combustion efficiency. Each cylinder had 2 spark plugs for redundancy and better combustion. The cooling system received continuous attention. As power output increased, more heat had to be dissipated. Improved coolant formulations and radiator designs kept temperatures under control. Rolls-Royce established a systematic approach to development. Combat reports from pilots and maintenance crews were carefully analyzed. Problems were identified, solutions developed, and modifications rapidly implemented. The feedback loop between frontline users and engineers was remarkably efficient. Ernest Hives insisted on maintaining close contact with the RAF. He wanted to understand exactly how the engines performed in combat. This user-focused approach drove continuous improvement. By war's end, the Merlin had gone through dozens of variants, each optimized for specific aircraft and mission requirements. Some versions prioritized low-altitude performance for ground attack aircraft. Others maximized high-altitude capability for fighters and reconnaissance planes. This flexibility made the Merlin suitable for a wide range of applications. The engine's evolution demonstrated the importance of iterative design. The best products are not created in a single stroke of genius, but through continuous refinement based on real-world feedback. As the war expanded, it became clear that Britain alone could not produce enough Merlins. The solution was to manufacture the engine in the United States. The Packard Motor Car Company was selected to build Merlins under license. Packard was known for quality automobiles and had engineering expertise. But building aircraft engines required different capabilities. In 1940, a team of Rolls-Royce engineers traveled to Detroit. They brought complete sets of drawings and specifications for the Merlin. The task was to adapt British manufacturing methods to American practices. One immediate challenge was the difference in measurement systems. British drawings used imperial measurements with unique thread standards. American industry used different imperial measurements and thread standards. Every dimension had to be carefully converted. Material specifications also differed between the two countries. Alloys that were standard in Britain might not be available in America. Equivalent materials had to be identified and tested for suitability. American manufacturing emphasized even greater standardization than Rolls-Royce. Packard engineers suggested modifications to make parts more interchangeable. Some tolerances were tightened. Machining processes were optimized. These changes actually improved the engine in some ways. The collaboration between British and American engineers was productive. Each side brought different perspectives and strengths to the project. By late 1941, Packard was producing its first Merlin engines, designated V1650 in American terminology. These engines were virtually identical to British-built Merlins, but incorporated American manufacturing improvements. Production ramped up quickly at Packard's Detroit facilities. American industrial capacity was enormous compared to Britain's. Soon Packard was producing thousands of Merlins per month. These engines powered American-built aircraft for Britain, and eventually for the United States Army Air Forces as well. The most famous application of the Packard Merlin was in the P-51 Mustang. The Mustang had been designed as a fighter for the RAF. Initially, it was powered by an Allison engine. The Allison performed well at low altitude but struggled higher up. In 1942, someone had the inspired idea to install a Merlin in the Mustang. The transformation was dramatic. The Merlin gave the Mustang excellent high-altitude performance. Combined with the Mustang's efficient airframe and long range, this created one of the war's finest fighters. Merlin-powered Mustangs could escort American bombers all the way to Berlin and back, something no other fighter could do. This capability was crucial to the Allied strategic bombing campaign. The partnership between Rolls-Royce and Packard was mutually beneficial. It demonstrated how international cooperation could enhance military effectiveness, and it ensured that Merlin engines were available in the quantities needed. While the Merlin is most famous for powering fighters like the Spitfire, it was adapted for use in many other types of aircraft. This versatility was a testament to the fundamental soundness of the design. The Avro Lancaster bomber used 4 Merlin engines. This heavy bomber carried enormous bomb loads deep into German territory. The Merlins gave it the power to lift off with 10 tons of bombs, and the reliability to complete missions lasting 8 hours or more. Lancaster crews depended on their 4 Merlins to get them home. Even when damaged by flak or fighter attacks, the engine's reliability saved countless lives. The de Havilland Mosquito used 2 Merlins. This remarkable aircraft was built primarily of wood, yet it was one of the fastest aircraft of the war. The Mosquito served as a bomber, fighter, photo reconnaissance plane, and night fighter, demonstrating extreme versatility. Its speed, derived from the powerful Merlins, was its primary defense. Many Mosquitoes completed their entire operational careers without a scratch, simply because no enemy fighter could catch them. The Merlin also powered maritime patrol aircraft, such as variants of the Wellington and Halifax bombers. These aircraft hunted German U-boats in the Atlantic. Long patrols over water required engines of absolute reliability. An engine failure over the ocean meant almost certain death for the crew. The Merlin's dependability made these dangerous missions possible. Transport aircraft used the Merlin as well. Modified versions powered aircraft that carried supplies and personnel. These unglamorous but essential missions kept Allied forces supplied. Even experimental and specialized aircraft benefited from the Merlin. High-altitude reconnaissance Spitfires flew missions over 70,000 feet, with specially modified Merlins optimized for extreme altitude. Racing aircraft set speed records with modified Merlins, pushing the boundaries of what was possible with piston engines. The engine's adaptability came from its robust basic design. The core architecture could be modified for different requirements, without compromising fundamental reliability. This made the Merlin economical from a logistics standpoint. Maintenance personnel could work on Merlins from different aircraft types. Many parts were interchangeable across variants. Supply chains were simplified when one engine type served so many purposes. By war's end, Merlins had powered dozens of different aircraft types, in roles ranging from frontline combat to training and transport. Few engines in history have proven so universally useful. Behind every Merlin engine was a story of human dedication and skill. The engineers who designed it, the workers who built it, the mechanics who maintained it, and the pilots who flew with it. Ernest Hives led the engineering effort throughout the war. His practical approach and leadership were crucial to the Merlin's success. He understood that engines had to work in the real world, not just on paper or in ideal test conditions. After the war, Hives became chairman of Rolls-Royce, guiding the company into the jet age. Arthur Rowledge, the chief designer, retired during the war, but his influence on the Merlin's design was profound and lasting. The fundamental architecture he created proved sound enough to accommodate years of improvements and power increases. The factory workers who built Merlins came from all walks of life. Many were women who had never worked in industry before. They learned precision machining, assembly, and quality control. Their work was every bit as important as the combat pilots. A poorly built engine could kill its crew as surely as enemy fire. The workers understood this responsibility and took pride in their craftsmanship. RAF mechanics maintained Merlins under difficult conditions, often working outdoors in all weather, sometimes under enemy attack. They performed engine changes, repaired damage, and conducted preventive maintenance. Their skill kept aircraft flying when spare parts were scarce, and improvisation was necessary. Pilots developed an almost emotional connection to their Merlins. They trusted the engine with their lives every time they took off. Many pilots credited the Merlin with saving them, continuing to run when damaged, getting them home when they should have crashed. The distinctive sound of a Merlin at full power became iconic, a deep, powerful roar that represented hope and defiance. For civilians in Britain, that sound meant RAF fighters were overhead, standing between them and the German bombers. For occupied Europeans, it meant Allied bombers passing overhead, a reminder that liberation might be coming. The Merlin represented more than just engineering excellence. It embodied the collective effort of a nation at war. Every person involved in its creation and operation was contributing to the fight for freedom. This sense of purpose elevated the work beyond mere manufacturing. It was a vital part of the war effort, and everyone involved knew it. Looking at the Merlin from a technical perspective reveals why it was so successful. The engine embodied several key engineering principles. First was the importance of fundamental design soundness. The basic architecture of the V12 configuration was well chosen. It balanced power density with mechanical simplicity. More complex designs might have offered marginal advantages, but would have been harder to manufacture and maintain. Second was the principle of iterative improvement. The Merlin was not perfect when first introduced, but it had a strong foundation that could be continuously refined. Each variant incorporated lessons from the previous one. This approach is more effective than trying to achieve perfection initially. Third was attention to manufacturing and maintainability. The best design in the world is useless if it cannot be built in quantity, or if it requires excessive maintenance. The Merlin was designed with production and field service in mind. This practical consideration was as important as performance. Fourth was the integration of advanced features. The supercharger was critical to high-altitude performance. The two-stage system in later versions was sophisticated, yet it was integrated in a way that maintained reliability. Advanced features are only valuable if they work consistently. Fifth was the use of quality materials throughout. Rolls-Royce never compromised on material specifications. Even when wartime shortages made quality materials expensive, this commitment to quality paid dividends in reliability. The metallurgy of the Merlin was state-of-the-art. Alloys were carefully selected for each application. High-stress components used the strongest available materials. Heat treatment processes were precisely controlled. The manufacturing tolerances were extremely tight. Critical dimensions were held to thousandths of an inch. This precision ensured proper fit and function of all components. Quality control throughout the production process was rigorous. Inspections occurred at multiple stages of manufacture. Defective parts were rejected before they could be assembled into engines. The technical documentation was comprehensive and detailed. Maintenance manuals provided clear instructions for servicing. Parts catalogs ensured the correct components were used in repairs. This documentation infrastructure supported operations worldwide. The Merlin demonstrated that great engineering requires more than clever design. It requires attention to every aspect of the product lifecycle, from initial concept through manufacturing, operation, and maintenance. This holistic approach is what made the Merlin truly exceptional. When World War II ended in 1945, the Merlin's story did not end. The engine continued in production for several more years. Many air forces around the world operated Merlin-powered aircraft. The engine served in military roles well into the 1950s. Some Merlins were converted for civilian uses. Surplus engines powered racing boats, setting speed records on water. Air racing enthusiasts used Merlins and modified P-51 Mustangs. These racing planes competed in events like the Reno Air Races. Some Merlins were adapted for industrial applications. They powered generators, pumps, and other equipment. The engine's reliability made it suitable for these demanding uses. The lessons learned from the Merlin influenced post-war engine design. Although the engineers applied Merlin development principles to new designs, the emphasis on reliability, manufacturability, and continuous improvement became standard practice in the aviation industry. Rolls-Royce itself transitioned to jet engine production. The company's experience with the Merlin proved invaluable. They understood high-performance engine development and manufacturing. This expertise helped them become a leader in jet propulsion. Today, Rolls-Royce is one of the world's premier aero engine manufacturers, a direct descendant of the company that built the Merlin. The Merlin also lives on in museums and air shows worldwide. Restored Spitfires, Hurricanes, Lancasters, and Mustangs still fly regularly, their Merlins roaring as they did decades ago. These flying museums preserve the sound and sight of the Merlin in action, allowing new generations to experience this piece of history. The maintenance of these vintage Merlins requires specialized knowledge. A small community of expert mechanics keeps the engines running. They use original parts when possible, manufacture replacements when necessary. Their dedication ensures that the Merlin's legacy remains tangible. Not just a story in books, but a living piece of aviation history. Collectors and enthusiasts pay premium prices for original Merlin engines. A complete running Merlin can be worth hundreds of thousands of dollars. This reflects both their historical significance and their rarity. Many Merlins were scrapped after the war when they were no longer needed. Those that survive are treasured artifacts of aviation history. The Merlin's influence extends beyond aviation enthusiasts. Engineers study it as an example of successful complex system development. Business schools use the Merlin story to teach about innovation, how to balance performance with reliability and manufacturability. Military historians recognize the Merlin as a war-winning technology, not a weapon itself, but an enabler that made effective air power possible. Without the Merlin, the Battle of Britain might have been lost. The bomber offensive against Germany would have been far less effective. The war might have lasted longer and cost more lives. The legacy of the Merlin is a reminder that technology, properly developed and applied, can change history, that engineering excellence matters in ways that extend far beyond the workshop, that the dedication of engineers, workers, and maintenance personnel can contribute as much to victory as the courage of combat troops. The development of the Merlin engine offers valuable lessons about engineering. These principles remain relevant today, decades after the engine's creation. First, start with sound fundamentals. The Merlin's V12 configuration was not revolutionary, but it was a proven layout that balanced competing requirements effectively. Trying to be too clever with basic architecture can backfire. Sometimes the conventional approach is conventional because it works. Second, plan for evolution, not just initial deployment. The Merlin doubled its power output over its operational life. This was possible because the basic design had room for growth. Engineers who only optimize for current requirements create dead ends. Those who design for future expansion create lasting products. Third, test relentlessly under realistic conditions. The years of testing before and during the war were crucial. Laboratory tests could not reveal all the issues that emerged in combat. Real-world feedback drove continuous improvement. Products that are not thoroughly tested in realistic conditions will fail. Fourth, listen to your users. Ernest Hives maintained close contact with RAF pilots and mechanics. Their feedback informed design improvements and operational modifications. Engineers who ignore user input miss opportunities for improvement. The end users understand the product in ways designers cannot. Fifth, never compromise on critical components. Rolls-Royce used the best materials available for stressed parts. They maintained tight tolerances on critical dimensions. Cost-cutting on essentials leads to failures that cost far more in the long run. Sixth, design for manufacturing from the start. A brilliant design that cannot be mass-produced is ultimately useless. The Merlin had to be buildable by thousands of workers, with varying skill levels using available machine tools. Manufacturability was as important as performance in the design. Seventh, design for maintainability. Field mechanics had to service Merlins with limited tools and facilities. The engine was designed so common maintenance tasks were straightforward. Products that are difficult to maintain will not achieve their potential, no matter how good they are when new. Eighth, document everything thoroughly. The Merlin had comprehensive technical documentation. Manuals, drawings, parts lists, all were detailed and accurate. This enabled effective support across the globe. Good documentation is as important as good design. Ninth, embrace collaboration. The partnership with Packard brought American manufacturing expertise. Working with the RAF provided operational insights. No single organization has all the answers. Collaboration multiplies capabilities and accelerates progress. Finally, maintain a culture of continuous improvement. The Merlin team never stopped refining the engine. Each variant incorporated lessons from previous ones. Organizations that become complacent fall behind. Those that constantly seek improvement remain leaders. The scale of Merlin production during World War II was staggering. Over 160,000 Merlin engines were manufactured by Rolls-Royce in Britain and Packard in America. This represented one of the largest production runs of any aircraft engine. The peak production rate reached thousands of engines per month. At times, a new Merlin was completed every few minutes. This industrial achievement required coordination on a massive scale. The workforce involved in Merlin production numbered in the tens of thousands, from raw material suppliers to final assembly workers. Each engine contained approximately 10,000 individual parts. Multiply that by 160,000 engines, and the logistical complexity becomes apparent. The engines powered approximately 40 different aircraft types, though the majority went into Spitfires, Hurricanes, Lancasters, and Mosquitoes. These aircraft flew millions of combat sorties, accumulating countless hours of operation. The reliability statistics were impressive. Merlins typically operated for hundreds of hours between major overhauls. Many exceeded their designed service life significantly. The failure rate was remarkably low for such a complex machine. operating under extreme conditions. The power output progression tells the story of continuous development. Early Merlin Mark I produced about 1,000 horsepower. The Mark 61 with two-stage supercharging produced 2,000 horsepower. This 100% increase came from the same basic displacement, achieved through improved supercharging, higher compression, and better fuels. The weight of the engine increased much more modestly, from about 1,300 pounds to 1,600 pounds. This meant power-to-weight ratio improved dramatically, a critical metric for aircraft performance. The fuel consumption at cruise power was relatively efficient, allowing aircraft to achieve good range. At maximum power, consumption increased significantly, but the engine could sustain high power output for extended periods. The production cost per engine decreased as manufacturing matured. Early Merlins were expensive to build, but process improvements and economies of scale reduced costs, making the engine economically viable for mass production. These numbers tell a story of engineering and industrial triumph, of a nation mobilizing its resources to produce a war-winning technology. The Merlin's production statistics represent more than just manufacturing. They represent determination, skill, and sacrifice. The Merlin did not exist in isolation. Other nations developed powerful engines too. Understanding the competition helps appreciate the Merlin's achievements. Germany's Daimler-Benz DB601 powered the Messerschmitt Bf 109. It was an excellent engine with fuel injection and good performance. The DB601 was competitive with early Merlins. However, it did not improve as much over time. Later versions of the Merlin surpassed German engines in power output. American Allison engines powered many early American fighters. The Allison V1710 was reliable and powerful at low altitude, but it lacked effective supercharging for high-altitude performance. This limitation made it less suitable for European combat, where engagements often occurred at 20,000 feet or higher. The American Pratt & Whitney R2800 was a radial engine, 18 cylinders arranged in 2 rows forming a circle. It was extremely powerful and reliable, powering fighters like the P-47 Thunderbolt and F-6F Hellcat. The R2800 excelled in rugged reliability, but radial engines created more drag than inline engines like the Merlin. This made them less suitable for fighters requiring maximum speed. Soviet engines like the Klimov series were derivatives of French designs. They were adequate but generally less powerful than the Merlin. Soviet aircraft compensated with lighter weight and different design philosophies. What made the Merlin stand out was its combination of attributes: high power output, excellent altitude performance, good reliability, compact dimensions, and suitability for mass production. No other engine matched all these qualities as well. The Merlin's adaptability also set it apart. It successfully powered everything from agile fighters to heavy bombers. Few engines proved so versatile. The continuous improvement program kept the Merlin competitive. While some enemy engines stagnated, the Merlin kept getting better. By war's end, it was among the most powerful piston engines in service. This competitive analysis reveals an important truth. Victory goes not just to the best initial design, but to the team that can continuously improve and adapt. The Rolls-Royce Merlin engine stands as one of history's great engineering achievements. It helped win the Second World War by powering the aircraft that defended Britain, bombed Germany, and escorted Allied bombers to their targets. But the Merlin's significance extends beyond its military contributions. It demonstrated principles of engineering excellence that remain relevant today: sound fundamental design, iterative improvement, attention to manufacturing, listening to users, never compromising on quality. These principles apply to any complex technology development. The Merlin story is also a story of people: engineers like Ernest Hives and Arthur Rowledge who designed it, workers who manufactured it under difficult wartime conditions, mechanics who maintained it in the field, pilots who trusted their lives to it every time they flew. Each played a crucial role in the Merlin's success. Today, the sound of a Merlin engine still evokes powerful emotions. For those who remember the war, it recalls a time of danger and sacrifice, when the fate of freedom hung in the balance. For younger generations, it represents a connection to history, a tangible reminder of what previous generations achieved. The Merlin reminds us that technology, properly developed and applied, can be a force for good in the world. That engineering is not just about making things work, but about solving problems that matter to humanity. The 160,000 Merlins built during the war represented millions of hours of human effort, countless acts of skill, dedication, and sacrifice. That collective effort helped preserve freedom and shape the world we live in today. As we look back on the Merlin story, we see not just an engine but a testament to what humans can achieve when faced with existential challenges. When they combine intelligence, determination, and courage, the Rolls-Royce Merlin was more than a machine. It was a symbol of hope during humanity's darkest hour, a product of human ingenuity that helped save civilization, and its legacy continues to inspire engineers, historians, and anyone who values excellence. The Merlin engine, the heart of the aircraft that saved Britain and helped win the Second World War. A masterpiece of engineering that will never be forgotten.